Hello everyone. Today we're going to be using Fourier Transform properties as practical tools. By mastering a few key pairs and properties, you can solve complex problems without having difficulties or having to go and integrate or use the definition of the Fourier Transform. So my recommendation is please go to the textbook and check the pair table and the property table in page 228 and 229. You want to pause this video and you want to get a copy of the tables, get a handout. You're going to be using it for the exam before we move forward. Okay, so at this point, I will assume that you already have on hand table 5.6 and table 5.7. So the first example we're going to be using is time scaling. So it's asking us to find the Fourier transform of x of 1 equals the rectangular of t over 4. Okay, so rectangular poles, as we saw in a previous example, is just none other than an expression in here where you have a pulse, and this pulse has been narrowed by 4 units, right? So in this case, we have this 4 in here. So a is equal to 4. Okay, so we can use the property number 3, which is time scaling, which states that if we have an expression in here, well, this is 1 over 4, sorry. We have an expression in here, x x of t scale at factor a, it will be transformed into 1 over the absolute value of a times the Fourier transform of that pair. Okay, so in this case, we're working with a rectangular pulse, which is our property, is our pair number 5. Okay, pair 5 states that the rectangular pulse T is paired with sync of tau, well, not tau, sorry, omega divided by 2. Okay, so if we want to use the pair in this case, we're working with the rectangular pulse of t divided by 4, right? So its pair is going to be equal to 1 over 4 all absolute value times sync of in this case omega divided by 1/4 divided by 2. Okay, which simplified will be left with 4 sync of 2 omega. Okay, so as simple as that. So it's just a matter of using the properties that we have. Okay, let's move to the second example. Okay, so this example is modulation. Okay, so in modulation, you will be having a function x of t. Okay, this function is being multiplied, is being convolved by a cosine. So the cosine is going to create spikes. So if you remember, the Fourier transform of a cosine is just spikes, 2 spikes at its angular frequency, the positive and the negative side. Okay, so what's going to happen is we will work the modulation by converting the signal that is not cosine into its Fourier transform, but then it's going to be modulated through the cosine by having spikes that will be manifested, that will be displayed at the angular frequency of the cosine, right? So we already work what is the Fourier transform of the rectangular pulse, right? So if we're looking to find x2 of omega, then this is going to be equal to 1/2. We open parentheses in here, and we know that the Fourier transform of the rectangular pulse is sync, right? So sync of, in this case, will be omega minus 10, right? Because this is the angular frequency of cosine is 10, right? Omega naught is 10 radians per second, right? So sync of omega minus 10 divided by 2. This 2 comes from the property of the rectangular pulse, right? So this will be 1 spike, and then the second spike will be at sync of omega plus 10 divided by 2. Okay, And this will be pretty much the Fourier transform for this modulation problem. Okay? All right, let's move to the third one. This third example is a convolution. Okay, so this convolution, we know the properties of convolution and how hard it is, right? So in convolution, we actually need to apply an integral, and we need to flip one of these guys into tau, and to negative tau, right? And then apply the convolution formula. But similarly, like the Laplace transform, the Fourier transform allows us to convert the convolution operator into a multiplication, right? So now, if you are able to find the Fourier transform of both functions x1 and x2, then you can convert them into the frequency realm and then just multiply them both and get the result in a very easy way. Okay, so in this case, they're not asking us to find the time version of it, right? As in y of t. They're asking us just to find what is y of omega. So in that case, we just multiply. Okay, so this is pretty easy. Again, I'm hammering in here with the rectangular function because it's really useful. So if we want to find individually x1, for instance, x1 of omega, which is the rectangular pulse, we know that this guy will be just sinc of omega divided by 2. And then if we're looking to find x2 of omega, then this will be sinc of omega divided by 2. But if you notice, there is a delay factor here. And then this is a time shift property. We use the time shift property, right? Which is our property number 4. So in here, what we do is that we multiply this term by an e factor, which will be stated by the number of elements that we're delaying, right? In this case, is a 1, right? So that's how we write a 1 in here. So meaning, if that rectangular pulse was delayed 2 seconds, then we will have e to the negative j2 omega. But in this case, it's only 1 second, right? So y of omega is just going to be x1 of omega times x2 of omega. Meaning, in here we'll just be multiplying sinc of omega divided by 2 times sinc omega divided by 2 times e to the negative j omega. So the result, y of omega, is just going to be equal to sinc squared of omega divided by 2 multiplied times e to the negative j omega, right? So as you see, using the Fourier transform simplify things pretty much. So instead of working with the definition, we can use the properties to simplify the mathematics of what we're actually trying to find. All right. So the next example I want to work is what we call duality. So duality is a property that is not in the book, but is extremely useful. So the property states, and I want you to look at this in this perspective. So if we have a pair where we have a function x, lowercase x of t, its pair is going to be capital case X of omega. But here's what the duality property says. Let's say we have a time signal that its shape is very similar to the right side of the pair, right? So the shape of X of t actually looks like X of omega, right? So what this property is saying is if our time signal looks like this side, then we can actually pair it so that it looks like the left side, but in terms of omega, in terms of negative omega, and multiplied by a 2 pi. Okay, so let's work this example, for instance. And before jumping into solving it, I want you to pause this video and try to check on the pairs on table 5.6 what expression looks like this one. All right, so if you check on your pairs, you might find that the pair number 4, it's what it looks like, which is the signum function, right? So signum signum, which we usually abbreviate by SGN, signum of t, its pair is 2 over j omega. Okay, so signum, if you remember from circuits, it's a function that just switches from -1 to 1, right? So this function is actually happening from -1 all the way to 1, right? So here we have a -1 and here is a 1. So this is signum, right? And then that's the property in how it behaves, okay? So what we have in here, so let's try to use the duality property with 2 j omega, okay? So in this case, what we'll have is that signum is equal to 2 j omega. So if we flipped, let's say we flipped and we say, okay, the duality property states that I want to flip and I want to say, okay, 2 over jt, right? So instead of omega, I flip to t, right? So what this is saying is that 2 over jt, its pair is going to be 2 pi signum of negative omega. That's what the duality property is stating, okay? Because this guy in here has the shape of this guy in here, right? So like what I have in here and what I have in here, right? So these two have the same shape. So its pair is going to be on the opposite direction, right? So the pair of this one looks like this one, right? It looks like the one on the left side, right? So in that sense, if this is a pair, right, then the duality pair looks like reversed, right? But it has two different elements, which is this 2 pi and this negative sign in here. Okay, so with that being said, it's just a matter of transforming what we want. So if you notice, it's a 1 over j pi t. How do we get that? So I think in here is just a matter of dividing everything by 2 pi. So this guy here, I'm going to multiply it times 1 over 2 pi. And then the other pair, I'm going to do exactly the same. And I'm going to take that sign out because if you notice, our signum function is actually an odd function, right? So I can actually take this negative sign out of it. And then I'm going to multiply this over 1 over 2 pi. By doing that, the 2 cancels with the 2. And then I'm left with 1 over j pi t, whose pair is none other, and these two guys cancel, as negative signum of omega. So this is an application of the duality property. So if you don't have, so what this is saying is, if your expression, the function that you, or the time signal that you're trying to convert from the time domain to the frequency domain doesn't look like any of the pairs on the left side, you can use the one on the right side by applying the property, the duality property. Okay? All right, so we have the last example, which is the usage of derivatives to find the Fourier transform. And this is a really nice example because it has a very graphical property and a very useful one. So in this case, they're asking us to find the Fourier transform of the triangular pulse function. And they're asking us to find what is, okay, so I didn't specify in here very clearly, but they're asking us find the Fourier transform of the second derivative of the triangular pulse. Okay. All right. So how do we do that? Okay. Before jumping into finding the transform, let's see this function graphically, right? So graphically, a triangular pulse looks like this. Okay, so it's a triangle that pulses from -1 to 1. Okay, so this will be what we call our function, our signal, right? So if we want to find the first derivative, right? So this is, we can call this one the primitive. if we want to find the first derivative, or delta prime, right? So we remember this from calculus, and what this look like is there's a 1 in here, right? Because the slope in here is 1, and then the slope in here is -1, right? So let me draw this in black so that we can actually see the difference. So from -1 to 1, right? You only see you can only see here the slope, right? So the slope of the left side is 1, right? Because it's a line with a positive slope, and then it switches to -1, right? So this is what we call the second derivative. Sorry, the first derivative, right? And then so this looks. So I want you to look this guy's actually looks like a unit step, right? This guys, they look like a unit step. So if we want to find the second derivative of the signals, then what we will see is the following. So as we move here with the unit step, you will have a impulse response, an impulse response that is happening at -1, right? Because that's where you have a rise, right? Then you will have 2 rises going down in here, right? So meaning this kind of sorry, not rises, but it goes down 2 units, right? And this looks like 2 times an impulse response, and then back at 1 it goes and rises again to 0, right? So you have another impulse function moving upward, right? So what I'm trying to say in here is that the second derivative of the triangular pulse, okay, looks like an impulse function at t plus 1, right? So an impulse function t plus 1, then you add, or in this case subtract, because it's going down, right? Minus 2 times an impulse function at t plus an impulse function at t minus 1, right? So this is actually the second derivative of it, right? So now what I'm going to be doing is I'm going to be applying the 7th property, the time nth derivative. So what I'm going to be doing is I'm going to apply a Fourier transform on the whole equation, so delta double t, and then I'm going to use a Fourier transform in here as well. Okay, so what this is going to be looking like is, so this sign in here will look like negative, j omega squared, right? Using the property, right? So in here, this is a 2, right? This is a 2, and this is a 2 of, I'll call this one x, just x of omega, right? And then to the other side, the Fourier transform of this guys in here are the following, right? So it's going to be e to the j omega, and this is using the pair 1a, right? Then we have -2 using properties using pair 1, right? And the last one will be plus e to the -j omega. Okay, so we work on a little bit on the left side. We know that j squared is -1, so this is like having negative omega square x of omega. And then if we pair together the exponentials, you will start noticing that they look very alike to one of the equations of our friends, right? Euler's equation, right? So, but before working that, we can simplify this a little bit and just solve for x of omega, right? So we have this e j omega plus e to the negative j omega minus 2 over omega square, and this is a negative, right? So we can actually convert this guy into a cosine, right? So this will be like having 2 e j omega plus e to the negative j omega divided by 2 minus 2 over negative omega square, right? So this is like having x of omega equals to 2 times cosine of omega minus 2 divided by negative omega 2. And with that, we complete the conversion, the transformation from having the triangular poles into this expression in here, right, by using the derivative property. All right, so I'm gonna stop here. All right, so but remember that there's quiz on Friday, and please practice the homework that there is that I posted in Blackboard. And if you have any questions, please email me or just come to office hours. All right, see you around.